In the last video, we have talked about the different phase relationship of soil. In this video, I will discuss the classification of soil. Okay, so classification of soil is today's lesson. Now, why classification of soil is needed? Well, you have already learned how your soil is formed. Let's say this is a mountain. Okay, there is a river like this, and it brings some big types of rocks. Okay, and then with due course and due to the action of water, this disintegrate like this into smaller fish, and again when it comes to your plane, it again disintegrated. Okay, and ultimately it form your silt and soil or clay, silt and clay like this. Okay, so all of these are soil. This is also soil, this is also soil, these are also soil. Okay, now as an engineer, if I ask you which type of soil is present in this region, obviously you need to have some word or a code word or a specific term to describe this particular soil. Okay, that's why this is very much important to classify each type of soil. Now the question is, how we can classify a soil? What are the criteria? Well, there are mainly two simple criteria based on which we, the civil engineer, classify our soil. The first criteria is obviously the size of grain. Okay, this is the first criteria and very simple criteria. And the second criteria is, well, we need a second criteria? If it is not sufficient, the size of grain is not sufficient. Let's see, let's say this is the size, let's say this is your 100 mm. Okay, and this is, let's say, 80 mm. Let's say these are your 20 mm. Okay, let's say this is 4 point, or let's say this is simply 4 mm, and these are, let's say, very fine particle, let's say 75 micron. Okay, so if I describe each and every one by this size, we can classify this particular shape or soil by this range, or this one with this measurement. Okay, so there is no problem in doing so, but the problem arises when this size reduces beyond 75 micron. Okay, so let's say there are soil particle here which have, let's say, size is only your, this is 0.075 micron or 0.75 micron or 0.075 mm, and this particle have, let's say, 0.002 mm, and again let's say there are another particle which are 0.001 mm. Okay, so when we try to classify this zone or these soils within this size range, this size is not sufficient to describe their property. Okay, it has been observed that if we try to describe this 0.002 mm particle soil, okay, and 0.001 mm, they vary a lot, their property varies a lot. Okay, which is not function of this size only, that is function of plasticity. Okay, this is function of plasticity. So based on these two particular things, first one is size of grain and second one is plasticity, we classify our soil. Okay, so in this video we will mainly concentrate on the size of grain here, and in the next video we'll talk about your plasticity. Okay, so what is size of grain and how Indian system specially classify your soil based on the size of your grain? In Indian system, there are mainly two type of soil. Okay, first one is your coarse soil. Okay, and second one is your fine soil. Okay, now what is the size which differentiate this coarse soil and fine soil? Well, the size is your 0.075 mm. This is the size which distinguishes between coarse and fine soil. Okay, so any soil above this size is known as coarse soil, and at the bottom or at the below of this size is known as your fine soil. Okay, so here you can see that if we take this as our reference point, there are tremendous number of sizes, and there are lots of number of or lots of type of soil which varies from 0.075 mm to your 100 mm or more than that, let's say 300 mm. Okay, so that's why again we subdivide coarse soil. Okay, so what are the subdivision of coarse soil? First one is your boulder. So when we will call any soil a boulder, when the size of the soil particle or grain is more than 300 mm. Okay, and next one is your cobble. What is the definition of this size? Well, when the size of your particle varies within this range 80 mm to 300 mm, we call that cobble. Next one is your gravel. Okay, so what is the range for gravel? The range for gravel is your from 4.75 mm to 80 mm. But for gravel, this range seems to be quite wide. That's why again we divide this gravel into subgroup. For range 80 mm to your 20 mm, this is known as your coarse gravel. Coarse gravel. Then from 20 mm to 2 mm, 20 mm to your, sorry, this is 20 mm to 4.75 mm. This is known as your fine gravel. So here globally the soil was classified into fine soil, coarse soil and fine soil, and here locally the gravel has been subdivided into two groups based on size. One is coarse gravel, another is fine gravel. Okay, based on their size. And after gravel come to the next one, that is your sand. Okay, so what is the range for sand? Okay, the range for sand is your, the lower limit was 0.075, so and the lower limit for gravel was 4.75. so if your particle ranges between 4.75 mm to your 0.075 mm, you call this particle of soil as sand. Again, this range seems to be quite wide, so we will, just like gravel, we will subdivide this range into three groups. First one is coarse sand, that varies from 4.75 mm to 2 mm. Next is medium sand, that is 2 mm to your 0.475 mm, or it may be 4 to 5 mm. Okay, and last one is 0.425 mm to your 0.075 mm. This is known as your fine sand, this is your medium sand, and this is your coarse sand. Okay, so we have classified all the soil which are under coarse category. Okay, so under coarse category we have total 1, 2, 3, 4 major 4 type of soil. And let's see, in case of fine category, how many soils are there? In case of fine category, we have 2 types of soil. First one is what was lower limit? That is 0.075. So fine will be started from this range, that is 0.075 mm, to your 0.002 mm, and the particle which ranges in this zone is known as your silt. Okay, so this is silt, and the particle which are less than 0.002 mm or 2 micron, they are known as your clay particle. So in fine you have two, silt and clay, and in coarse you have four, sand, gravel, cobble and boulder. Okay, so when we ask you to describe or to define any particular size of soil, you can simply tell me that this is 20 mm range. Okay, this is your gravel. Okay, or this is within 75 micron and 4 mm. Well, this is your sand. So now you have some weapon by which you can describe your, or you have some tools, sorry for saying weapon, you have some tools by which you can describe your soil based on the size of your grain. Instead of saying the full name like gravel or sand or your silt or clay, you can say or you can write this soil by symbol also. For example, gravel can be denoted by your G. Okay, sand can be denoted by S, clay can be denoted by C, but silt is denoted by M. Why? Because you have already S for sand. That's why M is being used for denoting silt. These are the symbol for all these type of clay. Now you have size and also the symbol to define the soil. Okay, but the question is how you will get this size. Let's say 300, your 80 mm or 40 mm or 20 mm or 10 mm or 4.75 mm or your 0.075 mm or 0.002 mm. How you will get the size of the soil? Well, for getting this size, okay, you need to sieve your soil. Let's say this is a big jar, and within this jar there are all type of soil particle. Okay, let's say this is your, what is the maximum size, that is greater than 300. Okay, so it is your boulder, and let's say this is the cobble, that is 80 mm. Let's say this is your gravel, let's say 40 mm. This is 20 mm. This is 10 mm. Okay, and let's say this is 5 mm. This is 1 mm. Like that, all type of soils are there within this jar. Okay, and the lowest size is your, let's say that is only less than 0.075 mm. Okay, so you have both coarse aggregate here, coarse soil, as well as your fine soil within this jar. Now you have to classify, or you have to quantify which size have which percentage. Okay, and based on that we can classify our soil, whether it is gravel or sand or silt or clay. So for that, what you have to do, you have to sieve this soil, this composite soil. Okay, and for that you will have some sieve with standard size based on the standard. Okay, this is the sieve, and it in plan it will looks like this circular, and here you can see that there are lots of opening based on the sieve size. Okay, let's say this is your 80 mm sieve. Okay, I'm just taking it arbitrarily, so the opening will be large, and so large so that the 80 mm particle, less than 80 mm, says there is a 79 mm particle which will pass through this opening. That's why that's why this sieve is designed. Okay, let's say we have a sieve which have size, let's say, for 0.075 mm. This sieve will pass the particle which have size less than 0.075 mm or the soil which are fine, and for that the opening will be very small. Okay, the opening will be very much small compared to this one. So in this way you will collect all the sieves like this, and you will arrange them to make a nest of sieve in such a way that the larger size is at the top. Let's say this is 80 mm, let's say this is 40 mm. I'm taking this value or number just arbitrarily for your better understanding. It is not from any standard. These sizes are given on your standard. If you use your Indian standard, these sizes are defined and you have to use that particular sieve size. Okay, and let's say this is 20, this is 10, and this is 5, this is your, let's say, 0.075, like that. Now one thing I would like to say here, how the sieve sizes are standardized in your standard code, or what is the basis of this size. Okay, the basic is when you plot the grain size distribution in a graph, that should be plotted in an equal interval. Okay, let's say if this is the size, let's say this is 20 mm, this is 10 mm, this is 5 mm, and this is your, let's say, 1 mm. Okay, now in grain size distribution curve, this x-axis is in logarithmic scale or log scale. So when it is in log scale, to make the equal spacing of them, the value should be in such manner that when you take the log of them, the log 20, log 10, okay, log 5, the interval between them is more or less equal. You can check it. Okay, log 0.075, the interval between them is more or less same. That's why here you get the equal spaces between them. Okay, so this is the logic behind the sieve sizing. Now you take all the particles here. Obviously the smaller particles less than 80 will come down here. So here you will get quite comparatively smaller particle, and here you will get the least size particle. Okay, so this is the sieving. You have to simply shake this system until all the pan or all the sieve get its weight as constant. After that, what you have to do, you have to simply do one thing. Let's say you have taken total 10 kg of soil. Okay, and this is your 80 mm sieve. Okay, this is 40 mm, this is 20 mm, this is 10 mm, like that. Let's say this is your 5 mm. Okay, so you have all these sieves, and now you are, after completing the sieving process, you are measuring the weight in each sieve. Let's say here the particles are weighing your 3 kg. Okay, here your particles are weighing, let's say, 2 kg. Okay, here your particles are weighing, let's say, again 3 kgs. Okay, and here your particles are, let's say, these are more finer. These are again, let's say, this is 3 to 5, 5, 3, 8, let's say 1 kg. And finally here, let's say you have 1 kg. Okay, you have completed the sieving procedure. So if we consider 80 mm size, okay, So what is the cumulative weight retained here? That is 3 kg. And what is the cumulative weight in 40 mm size? This is 3 plus 2, 5 kg. What is the cumulative weight in 20 mm? Cumulative weight means all the weights above this sieve size. Okay, so here this is 3 plus 2, 5 kg plus 3, that's give you 8 kg. And similarly here, after addition 1 kg with 8, you give 9 kg, and here after addition of 1, here the total weight is 10 kg, and you have taken total soil as 10 kg, so it is okay. Now if this is the total weight retained by 80 mm size, so what is the weight of material which have passed through it? Obviously the total weight minus the retained, that is 10 minus 3 is equal to 7. And for this size, what is the material passed? This is 10 minus total retained, that is 10 minus 5 kg. What is the total material passed through this size? Well, this is 10 minus 8, that is 2 kg. Here 1 kg and here 1 kg. And here 10 minus 9, that is 1 kg. And here also 10 minus 10 is equal to 0, because this is the last sieve after which there is no particle. Okay, let's say you have in this system the least size or least diameter of particle is 5 mm. Okay, so there is no particle remain which will pass through this. That's why the passing is 0. If we consider or if we express this value in percentage, we'll get 7 by 10 times 100, so 70%. Here this is 50%, here this is 20%, here this is 10%, and here this is 0%. So what is the value indicate? 10% is the weight of this total soil which passed through this particular size. Or if we say that 70% of passing means in this soil there are soil material which are 70% in weight which can pass through this size. Now if you plot them in graph, let's say this is your graph, clear, and this is in log scale, and this is plain arithmetic scale, and this represent the percentage of passing. That means this percentage which is passed, and this indicate your size. Let's say this is your 5 mm and this is 10 mm. This is in log scale, that's why they are in equal interval, and this is, let's say, 20, 40, 80, and in our case 80 mm was maximum. Okay, so for 80 mm, the percentage of passing is 70%. Let this is 10, 20, 30, 40, 50, 60, 70, and 80, 90. Let's say this is 100. So 70 is 10, 20, 30, 40, 50, 60. This is your 70%. So corresponding to 80 mm, we'll get our 70%. So this is the first point you are getting. Okay, this is the first point. Next, for 40 mm, the percentage of passing is 50%. Well, this is 40 mm, and here it is your 30, 40, this is your 50. So you are getting somewhere here like that. For 20 mm, this is 20%, then 10%, then 0%. So 0, here is your 10%, here is your 20%. This is a purely coincidence that due to 20 mm size, you are getting 20% passing. Okay, it may be 25%. Okay, and when you plot your complete, just draw them like this. you'll get a curve like this. Okay, and this curve is known as your gradation curve. Gradation curve, very important curve. This gradation curve define all this classification based on your size. Okay, once you are done with your gradation curve, you have to plot 3 salient point. What are they? First one is D10, second one is your D30, and last one is your D60. Okay, what is D10? D10 is known as the effective size of this soil. And what is D10? This is a size. It may be any size, 10 mm or 20 mm or 30 mm. Doesn't matter. Maybe 5 mm also. Or maybe your 45 mm, any arbitrary value. Okay. But if we pick up that point, let's say this is 30 mm. So it is somewhere here. So corresponding to this point, the passing should be 10%. So to get the passing, go to the curve, from the curve come back to the passing axis. So you are getting here, this is somewhere 30%, but you need 10%. So it is not correct. For 10% you will have 10 mm size. So here the effective size D10 is 10 mm. Okay, next one is your D30. Just like D10, you have to find D30. So pick up 30. 30 is here. Sorry, 30 is the percentage of passing. So here is 30. So come here to the gradation curve, and corresponding to this 30% passing, you are getting a size. Let's say this is your 20/40, let's say it is 30. Okay, or this is log scale, so this is, let's say this is 35 mm. So you are getting D30 as 35 mm. Similarly, you will get D60, which is the size corresponding to passing of 60%. Okay, so here you will get somewhere here, let's say this is your 48% or 48 mm. Okay, so D60 is 48 mm. Now the question is, why these values are required? Well, this effective size and this D30 and D60 define the gradation curve. How? Well, if we take D60 divided by D10, it will give me some values. For here 48 divided by your 10, that is 4.8. Based on this value, we can say whether this gradation curve is well graded or poorly graded. Okay, so what does it mean, well graded or poorly graded means? Well, well graded means that if you have a system of soil where you have all range of vertical, so this is a well graded soil. But if I tell you it is a poorly graded soil, that means, let's say it have a particle like this, then like this, then like this. Okay, so this is poorly graded or gap graded. Okay, this is poorly graded soil. Now, why this particular ratio define this well graded or poorly graded nature of this gradation curve? Well, that has been established from lots of thesis. That is not in the scope of this lecture. For right now, you have to find D60 and D10 because the ratio of them define whether it is well graded or poorly graded gradation curve. Okay, if this value, let's define this ratio as CU. Why CU? Here you can see this has varies uniformly, not abruptly. Okay, that's why this coefficient is known as uniformity coefficient. If the CU value is more than 5, this indicate that this gradation curve is well graded. Okay, so here this is 4.8, so it is not well graded curve. Okay, so that's why you have to find D60 and D10, and this is all about your gradation curve. Okay, but here I have not mentioned anything about the gradation of your fine particle. When you have a soil system like this, where all type of sizes are present here, initially when you have sieved it, you have taken only coarse particle, you have not taken fine particle for sieving. Why? What are the fine particle? The particle which are less than 0.075 mm in size. These are not able to pass through a sieve of such small size. Here the sieve size has to be 0.075, and obviously in fine, obviously there are some particles which are 0.002 mm in size or 0.001 mm in size. So the sieving is not efficient process for the gradation of this particle. For that you have to take them, this fine particle which are less than 0.075, in a solution. Let's say this is a water. Okay, and you have to mix a part of this fine soil into this water. Okay, let's say after mixing this becomes like this. Now you have to use a particular instrument which is known as your hydrometer. What is this? Hydrometer. This hydrometer coin looks like this. This is the tube and this is the jar like this, and here is the weighted part. It looks like this, and the readings are given. Here it is 0 and here it is 60. Readings are given here. When you insert this hygrometer here, let's say this, okay, it will give you some reading. Let's say this is your 25. The reading in hydrometer is 25. Now what does it mean by this 25 reading? Well, what you need for drawing a gradation curve? Well, a particle size. Let's say this is the particle size here. Let's say this is 15 mm. So you need a diameter of particle d, and you need the percentage of passing. Let's say 15%. So your requirement for drawing your gradation curve is the diameter of particle first, second the percentage of passing. Okay, so once you mix this soil within this water and you wait, let's say you wait for after mixing, you have mixed here your soil. Now you are waiting. After waiting time, let's say t. Okay, let's say you have waited for time t. What you will see? Well, you will see that some amount of soil has been settled here. At the top the water is clear. Okay, and as per Stokes law, the velocity in this type of solution is given as this formula, that is 1/18 mu g minus 1 gamma w d square. This is the Stokes formula, and from this formula the velocity is known as the distance travel L. Let's say this is L in time t. So L is known to you, t is also known to you, so you can find velocity, and from that formula you can calculate d of the particle which have traveled through this length. Or let's say initially the particle was here, now it has reached here. Okay, so you have got first answer, that is d. And how you will get the percentage of passing? Or percentage of passing means the particle size which are still present here and which have diameter d, let's say d2, where d2 is less than this diameter, this is d1. Okay, so that's the same formula in case of sieving. If this is the size for d1, you will get particle of less size d2 at the bottom, but here you are getting them at the top, just reverse case. The hygrometer is made in such a principle that it will give you this value, the percentage of passing. The detailed mathematics involved in this hygrometer technique, it's a total scope of difference lesson, or a separate video can be made on this. So these are the two things you have got, but one thing you need to make clear here, which are very much important for hydrometer, that is correction. What are the correction? There are three types of corrections which are involved in hydrometer. First one is, let's see, this is the jar. Okay, let's say this is the solution, plain solution. In this there is solution of soil. Now if you drop the hydrometer here, this is the hydrometer, this is the bulb. Okay, and you will take reading here, but it is not possible for you to take reading at this point, because you will see this like this. This is the tube, and the water will make a surface like this. So the hydrometer is scaled from 0 to 60 in downward. Okay, let's say you are supposed to see here 20, but due to this you will see somewhere here 18. So the correction is known as meniscus correction. This meniscus correction is always positive. Why? You are taking under reading. Instead of 20 you are taking 18, so the error is negative, correction will be positive. The second one is your correction due to deflocculation agent. What is deflocculation agent? When you are mixing the soil particle within this water, this soil particle try to coagulate, or they make a bigger particle together. If this is happened, you will not get exact reading. That's why you have to add some external agent. The known name is sodium phosphate. This will make your particle keep apart. Okay, this flocculation will not form. So obviously due to this addition, the density of the solution will increase. So initially, let's say the density was such that the reading was here, and it was, let's say, your 15. Okay, once you add this agent, sodium phosphate, deflocculation agent, and the density increases, so it will simply uplift. The hydrometer will be uplifted. That's why now this part becomes here, and your reading will be somewhere your 20, because the reading is from 0 to 60 towards downward. So instead of 15 you are getting 20, so error is positive, so correction will be always negative. This is correction due to deflocculation, deflocculating agent. Okay, so that's all for your gradation curve. In this video I have mainly discussed the gradation or the classification of soil based on particle size of grain. Okay, in the next video I will discuss how the soil is classified based on your plasticity.